Okay, once more onto the bridge, dear friends. So, this week I'm going to be giving 3 segments on eigenvalue problems. So to begin with, we'll just remind ourselves a little bit about eigenvalue problems. So traditionally we would have a matrix and then a column vector, and the eigenvector equation is this one. I've decorated my vectors with little twiddles underneath. Okay, so this is the problem that we're most familiar with, so I'm going to think about problems where we perturb this. So the perturbed version, we will have an ax equals lambda x plus an epsilon times something. Let's just call it b. Now to begin with, what we'll do is we will consider perturbed algebraic eigenvalue problems where that is our small parameter times another matrix and then this vector x. So this is the problem that we'll talk about, and if I discard the final term here, I've got a problem that's the same as this one. So that's the perturbed eigenvalue problem that we'll now talk about. So what's sort of novel in comparison to the previous problems we've been talking about, where we have dealt with perturbations of algebraic problems, is that now, as we're going through, not only are we seeking to find this vector x, but we also need to calculate the eigenvalue en route. And that'll lead to a few twists, as we shall see. And there'll be twists on the twists. And those will be the topics of the next 2 segments. The first segment will be just about directly solving this particular problem. Okay. So, I'm going to make some preliminary observations. That's always a helpful thing. Preliminary observations. If I put epsilon equals to 0, I'm going to get ax is equal to lambda x. So I'm expecting that x is an eigenvector, which we've called E in this canonical problem up here, and lambda will be the eigenvalue, which is called A there. Right, so that's the problem. Now, when we press on to next order, then what we will find is we'll get some equation for the corrections from here that are forced by this particular term. So ahead of time, you might anticipate that there's going to be a correction to this and a correction to this. So the next order problem is going to have 2 things in there that we're going to need to calculate at the same time. Just as in the leading order problem, this tells you what both the eigenvector and the eigenvalue is. So that's sort of the quirkiness of this particular problem. It makes it slightly different from the algebraic problems we've been dealing with. So let's attack it by putting in some kind of a series, so we'll use the expansion method. So here we go. So we've got the expansion method. We will say that x is equal to x0 plus epsilon x1 and so forth, and lambda will be a lambda 0 plus epsilon lambda 1 and so forth. So we take this and we put it into the equation. So we get a x0, and this in here I'll put on a line below, and then there's extra stuff. So this is the left hand side. Then here we get 2 terms. The leading order, there's a lambda 0, 1 term rather, x0. Make sure I should put my twiddles underneath. Then I get 2 terms at next order. So there's the lambda 1 x0, and then there's a lambda 0 x1, and there's also this term. And more stuff. right? So this is substituting this series into the equation and just organizing it line by line. So we've got the terms without epsilons, the terms with one epsilon, and then the rest, and we're going to just truncate this and solve this sequentially. Okay, so that's where we are. So this is following the scheme that we've been following for dealing with algebraic problems via the expansion method. Okay, so now I'm going to come back over here. This is the problem. The ink doesn't come off too easily here. Okay, so I'm going to translate this to the top, just to remind ourselves what we're doing. Right, so a leading order, the problem that we've stated over there, it's just these two, which is the same as this problem down here. So the epsilon to the 0 terms, that's a x naught is lambda naught x naught, and that's just the traditional eigenvalue problem. And so we would then say that x0 is equal to an eigenvector, and lambda 0 is the corresponding eigenvalue. Now, if A is n by n, that would lead you to expect that there are n choices for the pairs A and E. And what the expansion will do is it will take one of these pairs and figure out the corrections to it because of this perturbing term. So that's where we're going. And I have to do it for each pair independently. I pick one and run with it. So now we can ditch the preliminary observations. So I picked one of these. Now I'm going to go to the next set of terms. Those are the ones with 1 power of epsilon. And from here, I have a x1 equals to lambda naught x1 plus lambda 1 x naught. Oops, daisies. Plus b x naught. Okay, so that's the problem we need to solve, and as I mentioned before, from this problem we need to get both x1 and lambda 1. So how can we solve this? So let's just back off a second and think a little bit more about matrix algebra technology. So when we solve the problem like this, that's the traditional eigenvalue problem, it's usually cast in terms of a matrix, a column vector, and the eigenvalue. However, there's an entirely equivalent way of doing it where you think about row vectors. And the row eigenvector problem satisfies something like this. I've got a row vector, and just to distinguish the fact that it's a row rather than a column, I'll put a little dagger on it. So this, when I multiply from the left with my matrix, that's going to equal the eigenvalue again times the row eigenvector. So this is the row version of AE equals AE without the daggers. Okay? Now then, what does this mean? Well, let's just rearrange it a little bit. And it means that if I take E dagger and multiply it on this side by the matrix A minus big A minus little a times the identity. That's equivalent to taking that to this side, so that's just 0. That's the row 0 vector. All right, so this is the equation satisfied by the row eigenvector once I've put the corresponding eigenvalue in there. Right, now let's go back and look at my equation that I need to solve up here. So I'm going to take this to that side, and then bear in mind that lambda 0 is just a. So I have a minus this times x1 equals, well, it's the correction here, and x0 is e, and I have plus be. Okay, so far so good. Now you'll notice that this is exactly the same as this, so if I just come along and I multiply by that object, on the left-hand side here I'm going to have e dagger with the matrix product with that matrix multiplied on the right by x1, but this is just 0. So if I take this equation and I do the multiple from the left with the row eigenvector, the left-hand side will be eliminated, which is kind of interesting because what it will mean is that I ditch the bit of the equation here that has the x1s in there. What's left over are some matrix products on the right involving what I don't know in lambda 1. So by performing the operation of multiplying on the left by the row eigenvector, I'll eliminate the x1 and out will pop a formula for lambda 1. So I'm going to multiply by e dagger on the left. Okay, so having done that, I'm now going to arrive at an equation for lambda 1. So let's just write that down. At this stage, I don't need to know the... Ooh. Uh-oh. Beautiful. Okay. All right, so having done that, let's just go through to the result. And let's change color. So I've multiplied by the e dagger. The left-hand side gone away. I get lambda 1, e dagger multiplying e, plus e dagger multiplying be. That's going to have to be 0. So I'm just going to solve this for lambda 1. This is just some number, the multiplication of a row with a column vector. So that's a number. I'll take this term to that side and divide by it. This is my formula for lambda 1. Okay, so now I've found lambda 1. I can now say, okay, well, this is just a standard type of problem once I've figured out what lambda 1 is for x1. So then I'm going to solve a minus a I times x1 equals, and let's just call this thing the right-hand side there. So that's the last stage. So I break it down into these two different pieces. First of all, I calculate the eigenvalue correction. Then I calculate the eigenvector correction like that. So that's how it's going to work. Let's see it in action for a particular example. So the novelty here is the use of the row eigenvector problem. Otherwise, it's just using standard linear algebra. The way that you calculate the row eigenvectors is just the same sort of thing, though. It's algebra. Right. So here's my example. I'm going to take the matrix A to be 1, 1, 2, 0, 1, 0, 0, 0, 3. B, this is this perturbing matrix, that'll be 100, 1, 1, 0, 1, 1, 1. Okay? So, I'm solving the problem that I posed at the start. And the strategy will be to first of all write down the eigenvalues and eigenvectors of the matrix A, and then compute the corrections to them. So in order to do that, we first of all have to calculate the eigenvalues and eigenvectors. That is a little bit of a laborious exercise. It can be expedited by using the computer. Let me just cut to the answers and tell you what the eigenvalues and eigenvectors are. I have helpfully employed a triangular matrix, which tells you immediately that the diagonal elements are the eigenvalues. So, I know that, for example, A has eigenvalue little a is equal to 3, we take the last one, and the eigenvector corresponding to that is 1, 0, 1. So that's what we're going to call E here, right? That's the pair. I'm going to do a quick check. If I take that and multiply by that, I'm going to get 3, 0, and 3. So that's 3 times this. So that's indeed the eigenvalue eigenvector pair. Now you can also verify that E dagger, the row, is 0, 0, 1. So if I take this and multiply on the left, I get 0, 0, 3, which is 3 times that. So that's the basic information that I need about that one particular eigenvalue eigenvector pair. Now, I mean, I could go through the calculation all again. However, I've already written down that formula, so we may as well just use it. So I have BE, that's this bit, that's just this times this, which is 1, 1, 2. Now I need to then multiply by this object, this row eigenvector. So that's going to pick out 2. Now also I need the denominator here, that's just the product of E dagger and E, which is 1. So in other words, lambda 1 is minus 2. So that's the eigenvalue correction. What that means is that lambda is equal to 3 minus 2 epsilon and stuff we'd have to go on to higher order in order to calculate. So that's what we've got so far. Now the next point is to calculate the correction to the eigenvector. That's this. So let's do that. Okay, so it's just a little bit of linear algebra to pop in the details now. This is a standard problem. Most of linear algebra is, of course, solving a matrix times a vector equals another vector. And you want to figure out what the first vector is, which is exactly what we're doing here. A matrix times the vector that we want equals another vector. Right, this was, if we remember, that was lambda 1 times E plus BE. Okay, so we've got A minus lambda I, here's A, and we're subtracting 3 off the diagonal, so it's minus 2, 1, 2, 0, minus 2, 0, 0, 0, 1. That's subtracting 3. Oops. That's subtracting 3 from the diagonal. And I've got my x1, so that's got some components. Let's call them alpha, beta, and gamma. And on the right-hand side, we've got this thing. So that's minus 2 times E, 1, 0, 1, plus, now BE, that's this. We've handily kept it there. Okay, right, so that would be minus 1, 1, 0. The vector there. So this is solving this particular problem for x1. I'm well on the way. At this point, it should give me the answer. So I've got 2 gamma plus beta minus 2 alpha equals minus 1. I've got minus 2 beta is equal to 1. And the final one tells me that 0 is 0. No point putting that down. So at this point, you'll notice that I've got 2 equations for 3 unknowns. So the answer is not going to be fully determined. There's some source of non-uniqueness in there. This one's always going to tell me that beta has to be equal to minus 1/2. So I can add that into there, which tells me that gamma minus alpha, when I divide by 2, is going to be equal to minus 1/4. So one choice would be to say that alpha is equal to 1/4 and beta is equal to minus 1/2. Right, and that's by just simply picking that gamma is equal to 0. But then the non-uniqueness is that I can add any amount of gamma there. So the more general solution for alpha would be this plus gamma, where gamma is not known. So I find that x1 is equal to gamma 1, 0, 1 plus 1/4 minus 1/2 and 0. So that's the answer for x1, and it's not unique. It's got this piece in there, and you'll notice that that's just the eigenvector again. So we've got an arbitrary amount of the eigenvector, which is part of the solution for x1. Now that shouldn't be a surprise if we just go back and have a quick look at the problem that we solved for it. So the problem that we solved for it was exactly the following. A minus little a times I, x1 is equal to something, that was the right-hand side. Now, of course, if I take anything times the eigenvector and put it in there, this kills it, right? So this is like a homogeneous solution to that particular problem, and it's never going to be determined by solving it. Okay, so that's how you follow the procedure to calculate the correction to the eigenvalue, the correction to the eigenvector. Now, let's just sort of stand back a second and think about things a little bit more generally. So this is the particular problem that we're solving at this order, and remember that that was lambda 1 times x naught, which is E, plus B x naught. That was the problem we were solving. So if I have a matrix and I'm searching for this, this is, let's call it V. This is the standard type of matrix algebra problem. Matrix times vector is vector. You're solving this to get that vector. Right, so the way that you would do this formally is to invert your matrix and write the formal answer like that. So that's the inverse of the matrix. I multiply by that, and this is what I would get. So formally, that's the answer. Now you know that you can do this as long as this matrix M is invertible. That's equivalent to saying that the determinant of m is not equal to 0. But here we've got that the determinant of a minus lambda I, that's our m, that is equal to 0 because that's exactly the equation that tells you what the eigenvalues are. So we are in the bad situation of having to solve this particular problem where you've got a non-invertible matrix. And if you were just doing standard linear algebra, you would panic because you'd be worried that there's no way of then solving this. So we have to go back to the drawing board a little bit in terms of a general theory and figure out what precisely we're doing at this point. So we're not solving ax equals to b or mx1 is equal to v with an invertible matrix. So the standard linear algebra problem is not what we've been given. Instead, we've got this non-invertible matrix here because the determinant is 0. So in that situation, there are two options. The two options for solving the linear algebra problem are the following. If determinant of m is equal to 0, if it's not invertible, there are two possible cases. There's either no solution, or there's a magical situation where there is a non-unique solution. Most of the time you're not going to get any solution, but there are some very special situations where you arrive at a non-unique solution. Okay, well, here's the example solution that we found. It was indeed a non-unique solution. So there was a solution, it was not unique, so we're obviously in this second situation. So how have we been able to solve this particular problem with a non-invertible matrix to get to arrange that we're in this situation? Well, coming back here, this is the right-hand side. The thing in the right-hand side, on the first term, contains the lambda 1. So basically, what we've arranged here is we've demanded at this stage that we are going to be able to solve this particular problem, and we're going to essentially use the freedom in what lambda 1 is to make sure we're in this situation. So in other words, we have picked lambda 1 to ensure there is a solution for x1. So that's essentially what we've just done. So we've got a problem at this order, which in general, if I put any old lambda 1 in there, it wouldn't have a solution. But by carefully arranging things and picking lambda 1, we can solve it to get a non-unique solution. That's exactly what we've done. So, in general, you'll find this referred to as taking the Fredholm alternative. It sounds like part of the Bourne trilogy. So Fredholm, that refers to the fact that there's a theory of integral equations, and there is a certain kind of integral equation that's somewhat mathematically similar to this, and in general it's not going to have a solution unless you pick a scalar number which is equivalent to an eigenvalue suitably. So you demand that to be the case, you pick this in order to get the solution. That's taking the Fredholm alternative. Alternatively, there's another way of posing it. When you go through the procedure of picking lambda 1, now if we just go back and remember what that was coming up here, that was multiplying by the row eigenvector to eliminate the left-hand side, right? That gets rid of x1. That's the first thing that you think that you're solving for. We're actually going to solve for lambda 1 first. That's by multiplying by the row eigenvector, eliminating the left-hand side, and coming up with a formula for lambda 1, right? That's a solvability condition, right? Because by doing this, we're going to guarantee that we're going to get the non-unique solution. So this procedure of picking lambda 1 is a solvability condition. And so that's how it goes. Okay, so we've gone through the theory. There's something in the background here, Fredholm alternatives, it applies to integral equations. The solvability conditions. This idea of a solvability condition will recur in a number of different contexts in this course. Okay, so that's how you attack the most straightforward eigenvalue problem, and you may have guessed at this point that it's not restricted to algebraic eigenvalue problems because I've already mentioned something about integral equations. So let's now advance and consider a different kind of a problem. Let's actually consider a differential eigenvalue problem. So here's a differential eigenvalue problem. Right, so previously we had a matrix times x equals lambda x plus a perturbing term. So here we go again. I've got Ly is going to equal lambda y, and then I'm going to have a small term that's perturbing this thing. So I'll write that like this. Okay, so I'm now solving for y and lambda. And y is a function of x, and L and B are differential operators. So we can apply the whole technology to this particular problem. And I'm going to do it for a particular example. Let's do it for the problem d2y dx squared plus e minus v of x times y is equal to 0, and v will be v0 plus epsilon v1. Right, so this term up here, there's a v0. The v0 and the d2 by dx squared, that's related to what I'm calling L there. The big E here is really the eigenvalue, and the term here, that corresponds to this. Right, so that's the problem we want to do. Now I've written it like this in a suggestive form because this is exactly the kind of problem that you might be faced with in something like quantum mechanics. The reason why I've used V here is because I'm thinking about solving for the eigenfunctions in a potential well. V is the potential, and the reason why I've used E is because I'm trying to calculate the energy levels. So this is really the Schrödinger equation when you're actually solving it to calculate the energy levels of a particular potential well. Now, in general, for any old V, this is a second order non-constant coefficient equation, and you're not going to be able to solve it analytically. For certain choices of V, you might be able to. And when people started to do quantum mechanics 100 years ago, and were solving problems like this, they didn't have the advantage of the computer, of course, and so you made up problems where you put in some sort of a potential that you could solve analytically. And then people realized that maybe they could do a little bit of perturbation theory. So you put in something here that you know, and then you're changing it slightly. So by doing this and by looking at the perturbation theory, the known potential here, that gives you a known leading order eigenvalue, and then you can change it a little bit and calculate the eigenvalue correction. So this is a way of extending a whole set of different energy level calculations to more complicated potentials. Okay, so that's the sort of the background of a problem like this. And as you see, we have now effortlessly transcended algebraic problems. Okay, so what am I going to do? I'm going to follow the pattern. I'm going to use expansion. So I'll set y is equal to y0 plus epsilon y1, and so forth. I'm not going to go beyond that. And then I'm going to say E is equal to E0 plus epsilon E1. So I take this, I'm going to assume that I'm going to be able to solve the problem for the leading order, and what I'm really interested in is calculating these two things, and actually I'm going to focus mostly on E1. So let's do a quick example. What if V0 is actually a constant? I actually want to solve this particular problem. I need boundary conditions, of course, so let's pop them down here. So what I'm going to say is that y equals to 0 at x is equal to 0 and some big L. That's not the same as that curly L. Right, so that's the little well, and I've got 0 boundary conditions on the edge. It's like having some infinite barrier or something. So if v0 here was a constant, then the leading order problem is going to be y prime primed plus e0 minus v0 y, let's put the zeros on there, equals to 0. That's what I need to solve to begin with. Since this is a constant, and with those boundary conditions, I can immediately write something like y0 is equal to sine of n pi x over L, where e0 is equal to v0 plus n squared pi squared over L squared. And that's just by plugging it in. It satisfies the equation and the boundary conditions with that choice for E0. So these are all of the energy levels for n. There's 1, 2, and so forth. Okay, so that's going to be the leading order problem. So that's an example of a potential that you can solve analytically. And now we can solve more complicated potentials where it's not quite a constant because we can put something in there that depends upon position. So this is going to be a useful exercise to extend your repertoire of potentials. Okay, so we'll follow the same procedure now. We need to go to next order. We're going to calculate two things at next order. We need E1 and Y1. And the first thing is going to be to apply some sort of a solvability condition to calculate E1. Okay, so we can do that as follows. The equation for y1, when I take my expansions, put them in there and then collect together the terms with 1 power of epsilon, I get d2y1 by dx squared. Then there'll be something that looks like this, plus e0 minus v0 times y1 equals, so what's left over? Well, there's going to be the perturbing term, which came from the v here, so this is going to be v1 y0, and then there's going to be the minus e1 y0. And y0 is going to be something like that, and e0 like that. So that's assumed known at this particular point. Okay, so how can I solve this particular problem? Well, I need to take the Fredholm alternative. I need to demand things are solvable by imposing a solvability condition. That's the sort of the language. So how can I do that here? So I need to somehow take this equation and multiply it by something and essentially eliminate y1. Okay, well, how can I do that? So let's consider d2 by dx squared plus e0 minus v0. Let's consider that operator. It's currently acting on y1, but I'm going to multiply by y0 and then integrate from 0 to L dx. Okay, let's step back a second before I go through the mechanics of this. So why did I do that? Well, when we were doing the matrix eigenvalue problem, we had this operation where we took the eigenvector, the row eigenvector, and multiplied on the left. So here we're dealing with functions and differential operators. Somehow I've got to multiply equivalently by something on the left. And for the matrix problem, it was like doing an inner product. And so here we're kind of doing an inner product, but with functions. And so what we're essentially doing is we're taking a function, multiplying on the left-hand side and integrating. That's the function analog of what we're doing in the matrix problem when we're using row eigenvectors. And if I actually use y0 here, which satisfies that equation, you'll see that it accomplishes exactly what you need it to accomplish. Now, in order to do that, I'm going to have to start integrating by parts. Because what I want to do is I want to flip these derivatives over from the y1 to the y0 and then use this equation. So let's just have a quick look at that. By integrating by parts, this term here, only that term, it's going to be minus the integral from there to there, of dy0 dx, dy1 dx, that's integrating by parts, and then there's a boundary term, which will be plus y0 dy1 dx, evaluated at 0 and L. Right, so that's integrating this term by parts once. Now that's 0, because y vanishes at 0 and L. So I've got that y is 0 at x is equal to 0 and L. Now if I put my sequence, by the way, in there and do everything at the consecutive powers of epsilon, that tells me that y0 equals 0 at those 2 points, and y1 equals to 0 at those 2 points. So that's actually what the boundary condition information tells me. So using the first of these here, I can get rid of that term. Now I can integrate that by parts again. So I'm going to integrate by parts again. So now I'm going to integrate this. That will leave me with the y1 term. So integrating by parts again. I get d2y0 by dx squared times y1 dx from 0 to L. That's the integral term. And then there's another boundary term, which is minus y1 dy0 dx between 0 and L. But that's 0 again because of this. So this operation of multiplying by y0 and integrating now gives me the following. It tells me that I have y1 d2 by dx squared plus e0 minus v0 y0 dx 0 to L. So that's fully integrating by parts here. Flipping all of the derivatives over onto the y0 from the y1. This has to equal, what's on the left-hand side is v1 y0 squared dx minus e1, the integral of y0 squared dx. And these are all from 0 to L. Okay. All right. Brilliant. This is 0 because that is the equation for y0. So that's 0. So this is accomplished removing the left-hand side from the problem, leaving me with the formula E1 is equal to V1 y0 squared dx divided by the integral of y0 squared dx from 0 to L. And then, by way of an example, I could take that example where we had constant V0, y0 was a sine, so that's going to give me something like L over 2 when I do that integral. And then this numerator here is going to be whatever I get when I take the sine squared and I put in the function, the correction to the potential that I'm interested in. Okay, so that's taking the Fredholm alternative, applying the solvability condition, calculating the eigenvalue correction. Now, we still need to calculate the correction to y. We still need to solve for y1. So let's have a quick look at that. Now, it's not simply a question of doing linear algebra anymore because we've got these differential equations. So how could I possibly solve this equation? Well, it's actually straightforward because I know a homogeneous solution to this equation, because the homogeneous equation is just the equation for y0. y0 is a homogeneous solution. That's equivalent to actually what we pointed out earlier on when we did the matrix eigenvalue problem, when the solution for x1 contained an arbitrary multiple of the original eigenvector. Right? That was the homogeneous solution. We get the same thing here. There's going to be an arbitrary amount of the homogeneous solution in the solution for y1. But what we're more interested in at this stage is the particular solution. So let's find a particular solution to this. So we can use reduction of order or variation of constants, depending on what you would like to call it. These things are essentially the same technique. So y1, I'm going to say, well, here's my homogeneous solution. Normally I would have an arbitrary constant out front. I'm making that now a function of x. So this is just applying reduction of order or variation of constants. Okay, so I've got this, so I need the second derivative. y1 prime primed is either a y0 prime primed plus 2 a prime y0 primed plus a prime prime y0. I take that, I put that into there, and I observe that y0 prime primed plus e0 minus v0 y0 is 0. So that means that when I take this term and put it into here, it cancels with that one. And having done that, we'll realize that we've then got a first order equation for a primed, big A primed. So we've reduced the order. So that's where we're going with this. And we're almost at the end. There's one thing that I mainly want to do with this, since we can't make much analytical progress without choosing a particular V1. We're not going to select a V1. But what I want to emphasize, how in principle one could solve this particular problem, and then put our finger on how we've managed to solve it by picking the right E1. Okay, so we're going to use this with that in here. What's left over? We've got a 2a primed y0 prime plus a prime prime y0. That's what's left on this side. This equals to v1 y0 minus e1 y0. That's the equation with this put in. Okay, so if I come along here and I multiply this by y0 primed, y0, I multiply by y0, so I get 2y0, y0 primed, a primed plus y0 squared, a prime prime, that equals v1 minus e1 y0 squared. How's that helpful? Well, that's helpful because the left-hand side here is now d by dx of y0 squared a primed. Now I can just integrate. When I integrate, I find that y0 squared a is equal to some constant. Let's call it t, plus the integral of v1 minus e1 y0 squared dx. So that's just an integral of this thing. I can actually impose the boundary conditions here. So I have this boundary condition that I had written down there before, which is that I need the solution to vanish at 0 and L. So I'm going to pick this integration constant to guarantee that's going to happen. So I'll just do the integral from 0 up to x, v1 minus e1 y0 squared dx, and then I'm going to have to divide by 1 over y0 squared. Okay, now y0, right, remember, vanishes at the ends too. So at x is equal to 0, you have to be a little bit cautious to convince yourself that this is bounded. So as x goes to 0, this vanishes and that vanishes, and actually there's a y0 squared in there. So this vanishes quickly enough so that that stays finite. So we currently look like we have a good solution near x equals to 0. But there's another problem, which is that we also have that y0 is equal to 0 and x is equal to L. Well, in that particular case, then I have to be a bit nervous because this integral here may not vanish where y0 vanishes, i.e. at x is equal to L. However, if I now go back and I remember exactly the problem that I solved for the eigenvalue correction E1, it was exactly demanding that the integral from 0 to L of this object was equal to 0. That's how you pick E. So in fact, by demanding that E1 satisfies that, you guarantee that this thing vanishes when x is equal to big L, so you get a good solution for A. So that's the solvability condition all over again. We're seeing it explicitly in this technique of using reduction of order to find the correction to Y1. Okay, so that's the standard type of eigenvalue problem and the end of the first segment.